Hello and welcome to this third and final installment in this three-part video series where we're looking at how to derive nonlinear force deflection models for planar rigid body mechanisms. We've already gone through the fundamentals of kinematics and how to evaluate the number of degrees of freedom that a mechanism has. Today we're going to talk about mechanical advantage and finally bring everything together to derive force deflection models for several examples. Just a quick recap, we're looking at this primarily because the semester project requires design of a nonlinear kinematic system, the trailing arm suspension for the semester project. In Project Deliverable 1, you need to be able to answer this question: how does the vertical force of the tire contact patch vary with vertical suspension deflection? And you are tasked with, later on, designing a suspension system that meets the requirements for this force deflection curve. So why does this force deflection curve matter? Why do we have requirements on it? It influences the dynamic behavior of the car, both with respect to comfort and to handling. Another question here is, if we are using a linear helical compression spring in this suspension system, why is the force deflection curve at the tire contact patch nonlinear? It's due to the nonlinear kinematics, and another way of looking at this is the mechanical advantage between the tire contact patch and the spring. The compression on the spring changes with the position of the suspension, and that results in this nonlinearity. What are the next steps? We're going to next quantify mechanical advantage. We're going to look at combined kinematics and force analysis. We're going through several example problems that are relevant to Project Deliverable number 1. And then after this video in class, we're going to discuss the details of Project Deliverable 1. This is going to include going through an outline for how to derive the force deflection model, and also going through a MATLAB code framework that you're going to use in this deliverable. Let's talk about mechanical advantage. With linkages and mechanisms, input and output properties are an important design consideration. One way of defining mechanical advantage for linkages and mechanisms is as the ratio between output force and input force. For example, we can look at a simple mechanical lever. We can define the length to the left of the fulcrum as L1, the length to the right of the fulcrum L2, and we have an input force and we have an output force. To analyze this system, we can use a statics equation. We can sum the moments about the fulcrum and set that equal to 0. And with that, we can derive what the mechanical advantage is. At least in this position, the mechanical advantage is simply L1 over L2. Now we can ask the question, what if the lever was in a different position, but the input and output forces were still directed in the vertical direction? Let's sum the moments about the fulcrum again, set it equal to 0. But we observe that the position theta cancels out. And so again, the mechanical advantage is just L2 over L1. So in this case, no, the mechanical advantage does not change with lever position. Here's another question. What if we had different force directions? What if they were not parallel as they are in this case? Would mechanical advantage change with lever position? The answer is yes. The moment arm for each force will change as the lever rotates to different positions. A task for you then is to sketch this out and at least conceptually verify that this is the case. Okay, now let's look at nonlinear force deflection models. Now, thinking way back to the beginning of the semester, we covered this topic of buckling of columns in compression. We looked at different boundary conditions. We looked at, well, how many degrees of freedom does the system have? And one of the main concepts we reviewed was this idea of collapse due to elastic instability as opposed to yield, which connects more to crystal slip or dislocation. So collapse can occur at force values much lower than would cause yield if there is elastic instability. We looked at an ordinary differential equation to determine the critical load that would cause collapse. And then we did a little bit with post-buckling analysis, or in other words, after we get to the critical load and the deflections are large, what happens? The ordinary differential equation was linear, and the assumptions required for that equation are violated as soon as the deflections become large. So if we wanted to find out what happens after buckling begins, we needed some kind of nonlinear model. So what we did was approximated the force deflection behavior of a column in compression using a two-link rigid body model. So we had two links in series, connected with a revolute joint, and at that center revolute joint is a torsional spring with a linear stiffness of K. And we assume if it's deflected just a little bit to the side and we start to compress it, then we're going to have an applied moment that compresses the spring, but the spring resists. And so the question is, for each position, either the vertical deflection delta or the angular deflection theta, what is the load P? How does this load P vary with position? To solve this problem accurately for the original column, it would require numerical solution of a nonlinear partial differential equation. And we went through and solved the force deflection curve for the simple two-link mechanism. And so I'm mainly pointing this out to identify that you have already been exposed to this type of analysis. And now we're trying to generalize it and give you the foundation that you need so that you can do this for the suspension project for project deliverable 1. And then once you have that model, then you will be able to actually create the design, which is the requirement for project deliverable number 2. So this is what we did in deriving the nonlinear rigid body model. I'm not going to go through this in a lot of detail, but wanted to point out the basic process. One strategy here was to define both the load P and the vertical deflection delta parametrically in terms of the angular deflection theta. So we can identify what the applied moment is due to the load P, what the restoring moment is due to the elastic nature of the spring, and then look at equilibrium and start deriving, well, what is the load P as a function of theta, and then what is the vertical deflection delta as a function of theta. And so this requires both a bit of trig and also looking at statics equations. But at the end, we have this parametric definition of the force deflection curve, and then we can plot it and visualize it, see what's going on. This is what we saw. This rigid body model predicts that we will see stiffening behavior, or the stiffness, the slope of this force deflection curve increases as the deflection increases. But in class, you might remember, we saw what actually happens with an experimental force deflection curve. It does start to increase the slope, so we do see some stiffening behavior, but then it starts to soften. So what's going on here? And what's happening is at large deflections, the material starts to yield, and we get this nonlinear material behavior that leads to the softening. Okay, let's look at an example where we pull all of this together, and we'll go through it in a little bit more detail. Okay, this is a crank slider mechanism, and we have an input force on link 1 at the bottom left. And there's a pivot, a revolute joint, joint A, and so link 1 is going to rotate about joint A, but then it's connected through this revolute joint B to link 2, and then link 2 is connected to the ground through a pin in slot joint. Now remember, revolute joints are full joints, pin in slot joints are half joints. So assume we know what the input force is, and that input force always remains perpendicular to link 1. And suppose we are interested in a particular range of positions for this mechanism, and we're going to define that using theta 1. So we're going to assume theta 1, the angular position of link 1, is known. And we are tasked with finding the general functions, the output force as a function of theta 1, knowing what the input force is, and then the mechanical advantage, which we defined previously as output force divided by the input force. And in this case, in this system, the ratio of output force to input force definitely will depend on position. So this is a crank slider mechanism. It's similar to an engine with a piston and crankshaft assembly. The number of links, including the ground, is 3. The number of full joints is 2. The number of half joints is 1. So using Kutzbach's equation, we see that the number of degrees of freedom in this system is 1. Now, we've discussed this before, that you've seen kinematic analysis in previous classes, but in my experience, it seems that most students entering this course have really only looked at kinematic analysis, where we're looking at single particular positions and not entire ranges of motion. And we need more general models in this case. So we're going to look at what happens with this system through this entire range of motion with theta 1 ranging from 0 to pi. We can simplify the geometric description a bit. I'm going to define these quantities L1, L2, and L3. And theta 1 is the position of link 1, and theta 2 is the position of link 2. We want to relate the output force to the input force for any arbitrary position, theta 1. First step, let's see if we can relate theta 1 to theta 2. So we draw the associated triangles, we do some trig, we identify, oh, these guys are going to have the same height above this axis of movement for the slider joint. And then we can solve for theta 2. It's going to be a nonlinear function of theta 1, as well as the link lengths L1 and L2. Now we're going to move on to statics analysis. We need to draw a free body diagram for link 1. This input force F1, that's going to cause a torque about joint A, this pivot for link 1. And link 1 is connected at its top end to link 2 through a revolute joint. There is going to be a reaction force at that joint from the resistance offered by link 2. Because the revolute joint cannot exert any moments about its axis of rotation, we're only going to have a force exerted at the end, and it's going to be aligned with the orientation of link 2. We want to calculate the reaction force at joint B. We can resolve it into two different components. I'm going to call those RA and RB, where RA is perpendicular to link 1 and RB is parallel to link 1. I'm going to define the angle formed by RA and RB as alpha 1. With this, I can define RA as equal to R cosine alpha 1. Now here's a little bit trickier part, defining alpha 1 as a function of theta 1 and theta 2. I'd recommend that you have a look at this and verify for yourself that this is correct based on the geometry that I've described. Okay, now we're pulling multiple things together. We have alpha 1 in terms of theta 1 and theta 2. Well, we've already calculated theta 2, so we can plug that 1 into theta 2. We can cancel out 2 of the pi over 2 terms. And then now that alpha 1 is known, that can be plugged in to the equation for RA. Now, what is the torque and its relationship to RA and R? So if we know what the torque is, that's going to be equal to RA L1. Remember that RA is perpendicular to link 1. And then using the definition above for RA, we can calculate the torque at A as a function of the reaction force R. Let's go back up to the diagram at the upper right and identify that we can define the torque at A also equal to L3 times the input force. With that known, we can define the reaction force R as a function of L3, which is known, the input force, which is known, L1 is known, and alpha 1. And alpha 1 can be put in terms of theta 1 and theta 2. Both of, well, we know theta 1 and theta 2 can be defined in terms of theta 1. So now we have a way of calculating what the reaction force is. All right, now let's move to a free body diagram for link number 2. We have 3 different forces acting on it. At the pin and slot joint, we have the output force, and we can have a vertical reaction force acting on it. With that, summing all of the forces in the horizontal direction, we can define an equilibrium equation and then solve for the output force as a function of the reaction force R, which we know how to calculate, and theta 2, which we also know how to calculate as a function of theta 1. Now we can define the mechanical advantage, and it's in terms of everything that we know how to calculate. So keep in mind that some of these quantities, like alpha, they depend on position, and everything's going to depend on design, L1, L2, L3, for example. All right, so that's a complete derivation of the force deflection curve and mechanical advantage for this crank slider mechanism. We could take all of this now and enter it into MATLAB or something else and then plot the results. So here's the MATLAB code that takes what we just derived and plots the mechanical advantage as well as the output force and how the positions change as a function of position. You can download this MATLAB code from the course website. It's kinematics example number 1. This is the output of that MATLAB code, and we can see some very nonlinear behavior. The top plot shows output force, the middle the mechanical advantage, and then the bottom the end position, all as a function of theta 1. And we can see that the first 2 plots, the force and mechanical advantage, are relatively small and flat for most positions. But then as we get to the extremes of theta 1, we have a very large increase in both cases. Now, this example is really similar to a homework problem that you were assigned. There are some differences, though. 2 main distinctions. One is instead of an output force, we have a linear spring at the end of link 2. And also there's no overhang at link 1 past joint A. And instead of a force applied to link 1, we have a torque applied. The other big distinction that's going to make the geometric calculations a bit more tricky is that instead of joint A being right in line with the axis of the pin and slot motion, it's offset. There's this distance defined in the figure below, L3. It's non-zero, so that's going to make things a little bit more challenging. Okay, let's move on to example number 2. This is a simplified suspension model. This is getting very close to what you need to derive for project deliverable number 1, but it is simplified, and it is going to be quite a bit easier than what's involved with the project deliverable. So let's assume there's no overhang past this joint where a force is applied, and we're going to make some additional assumptions of symmetry. If force at the bottom joint is 0, this undeflected position or the 0G position, we're going to assume that the link length L1 is going to be the same as the spring length LS. So L1 is equal to LS when F is equal to 0. This is also the basis for the second kinematics problem in your homework assignment. In this video, we're going to derive almost all elements of it, but I'm going to leave one thing out, and that's your homework problem, to work through the one thing I leave out at the end. I've provided MATLAB code for this problem. The part that I am not deriving in this video, it is what we call P-coded, or it's MATLAB protected code. So you can use this P-coded function. You can see what the force deflection curve is, but you can't see inside the P-coded function. So your job is to derive what should go into the P-coded function, and you can use the P-coded function given to you to verify that what you derived is correct. And this is the same sort of approach that I use for project deliverable number 1. I give you all of the code, but pieces of it are P-coded, so they're hidden from you, and your job is to derive those yourself and replace the P-coded functions with your own functions, and then verify that your results match the results using the P-coded functions. Okay, let's go through the derivation for this force deflection curve. Let's identify a few things. When theta is equal to theta naught, and I'm defining theta naught to mean the position when the force is equal to 0, the undeflected position. As I mentioned before, the spring length is equal to L1, the link length. And then we also say that the spring angle, theta s, is equal to theta, the position of link 1, when we are at the undeflected position, or in other words, when theta equals theta naught. So theta naught, that's undeflected or 0G suspension position. The spring component Ls changes with suspension position. The spring compresses and gets shorter. So if we sketch out what it might look like in a deflected position, L1, the length stays the same, of course, but now Ls is less than L1, and theta is less than theta naught. So now we can start doing some calculations to see, well, how much has the spring deflected? We want to find the compressive force on the spring as a function of position theta. By the law of cosines, we can derive what the length of the spring is as a function of L1, L2, and theta. By Hooke's law, we can say that the compressive force on the spring is equal to the spring constant K times the deflection of the spring, delta S. So what's the deflection of the spring? Well, we look at the length of the spring in the undeflected position and then subtract off the length of the spring in the deflected position, and that is going to be equal to how much the spring has compressed. Now we observe that the length of the spring at the theta naught position is equal to L1, and so then this simplifies to the spring force being equal to K times the quantity L1 minus Ls at theta. Now we need to put the spring force in terms of the vertical tire position delta t. So how do we quantify delta t as a function of theta? Looking at the sketch here toward the bottom right, we can measure the distance between the bottom joint and the vehicle frame at the two different positions. So when we are at the undeflected position, the distance from the bottom joint where the force is applied, the distance between that and the vehicle frame is L1 sine theta naught. But then in the deflected position at some arbitrary value of theta, the distance is L1 sine theta. So the deflection delta t is the first quantity minus the second. Delta t equals L1 sine theta naught minus L1 sine theta. Or I can write instead delta t over L1 is equal to sine theta naught minus sine theta. And then I can solve for theta as a function of delta t. Now we can substitute theta of delta t back into the spring force as a function of theta to obtain the spring force as a function of the vertical tire deflection. So this is almost what we want, but remember, thinking back to the requirements for project deliverable 1, it's not the spring force as a function of tire deflection that we want. It's the vertical force of the tire contact patch as a function of the deflection that we want. So for your homework, your job is to determine the vertical tire force as a function of position, and then to plot the tire force as a function of vertical tire deflection. One hint for that, draw the free body diagram for the bottom joint. MATLAB code is provided for this. It's available on the course website. It's called Kinematics Example Number 2. And again, there is a p-coded element. So in the homework, you are supposed to derive tire force as a function of delta. I've given you the p-coded function, so you know what the correct function is. You just can't see inside of it. So if you can get your function to match the results from this code, then you know you've done things correctly. When we plot the spring force and the tire force as a function of tire deflection, this is what we get. So let's have a look at spring force first. It's a slightly softening spring, but the slope K really never goes to 0. However, if we look at tire force, we see a very different behavior. If we get above, it looks like it's just below 0.4 meters of tire deflection, the slope goes to 0. And you might recall, in this case, this is an unstable condition. So essentially what would happen if we go beyond this critical deflection limit, it's not going to require any more force to continue deflecting, moving the joint up vertically. And so it's going to be an unstable suspension. So in a mechanical system design, usually this is something that we want to avoid. We don't want to have this kind of instability that could result in a failure. To summarize part 3, we reviewed the need for nonlinear force deflection models for your semester project. We introduced the concept of mechanical advantage and how to quantify it. We reviewed the first force deflection model that we covered earlier in class when we were looking at a simplified model for post-buckling behavior. And we presented complete force deflection model examples both for a crank slider and for a simplified suspension problem. So what's coming next? In class, we're going to review the project deliverable 1 requirements. We're going to go through an outline for how to derive the force deflection curve. And I will also demonstrate the MATLAB code that you're going to be using for project deliverable 1, and that'll put you in a good position to complete this deliverable on time. Remember, this is a rather intense deliverable, so please be sure to leave plenty of time for getting this done. Thank you.